and maybe it'll be a little less loud. Okay, let's see. How annoying is this? Raise your hand if it's very annoying. Okay, who doesn't think it's annoying? Okay, then I think everything's fine. Okay, let me try this again, and this is, let's try a different thing. Is this better? Can you still hear me over the speaker?
Sir, yes, sir.
Yes, sir. So, okay, so this is still being recorded, or that's good. Okay, let me get set up. As far as the midterm, we are in the last stages of grading it. I am hoping that the papers will make an appearance about 2 o'clock here, and we will go over the midterm then. But there were a couple of things that needed to be dotted and crossed before we could give them back. Okay. Any questions about anything technical or logistical? Okay, there's no problem with the day today because we have covered everything that we knew about. We did on the midterm. We're going to now get into a new area which has to do with graphs, okay, and graph algorithms. And that is sort of a next section. And so we'll have another problem of the day starting next class. And we'll deal with that then. Any questions about anything in here? I guess homework 2, which is on sorting algorithms and stuff, that is, I guess, due on Thursday, if I am correct. Is that Tuesday? Today is Thursday. That means Tuesday. Yes. Any questions? Okay. So what I'd like to talk about today, we'll do that later, is talk about graphs. Because graphs are one of the big ideas in computer science. And there's a lot of, let me try to lower it one more time. Is this better with this audio? Okay. The graphs are really one of the big ideas in computer science. And there are, so learning how to do graph algorithms is one of the big things in algorithms. And what's funny is over the next couple of, this unit, till the next midterm, is going to have on it 2 subjects, primarily. One is going to be graph algorithms, which students think they find easy, but I find terrifyingly difficult. And later on, dynamic programming, which students find hard, which I find very easy. And I want us to try to understand why there is this difference here. Okay, so let's first just take a quick look. One reason why students think the graph algorithm stuff is very easy is because they have seen some things about graphs before. Most of you have taken, everyone in here taken a discrete math class where you went through what a graph is? Yeah, you all know what a graph is. You know about, how many people have heard of depth first search? Know what that is? Everybody knows that. Breadth first search, everybody knows it. Shortest path algorithms, most people claim to know it. Minimum spanning trees, okay? And in some sense, we're not going to talk about very much more in here than that. Okay, so in one sense you say, oh, you know everything, everything's fine. The truth is that graph algorithms is a very subtle thing. Okay, graphs and graph algorithms are very, what I would call subtle. Now, what does the word subtle mean? Okay, let's write this word down. Let's try this. Subtle. Subtle. What does subtle mean? Does anybody know what subtle means? Have an idea of what that word means in English? Okay, yeah.
There are a lot of unintuitive details that are actually important.
A lot of unintuitive details that are actually important. That's actually not a bad definition. Okay, it's something that is, the distinction between right and wrong is more slippery than it might actually be seen. Okay, and graphs are very, very complicated structures, and getting algorithms that really provably work right on all graphs is a complicated thing. Okay, this is one where proofs of correctness need to be done, and it's where incorrect proofs of correctness are very easy to do. Okay, so it's a field where it requires a certain level of care to work out algorithms. Now, fortunately, in graph algorithms, a lot of time, if you do things right, you should have very little need to design new graph algorithms, okay? Because what's interesting about graphs is they're a very powerful structure that occur in a lot of different applications. And the main important problems have largely been very well studied. And the way to think about graph algorithms, it turns out, is not so much about designing new algorithms as knowing what the right algorithm is, what the right problem that you're really trying to solve, and pulling out the algorithm that you need to do. So many of you know about, like we mentioned in here, about shortest paths. What is the right algorithm to solve shortest paths? Some of you know. How many dimensions? In graphs. How would you solve it? What would the name be? Okay, breadth first, depth first. Dijkstra. I've heard 3 different names. So figuring out which is the right one to apply is an important issue. Okay? But the bigger problem tends to be seeing that what you have is really one of these problems. Okay? And so what we're going to talk about today are the basics of graph algorithms. What is a graph? How do you represent it in a computer? What do you call things? Okay? And what are the kind of properties of graphs that help you understand what kind of the right thing to do is? Okay, so what is a graph? A graph, as computer scientists think about it, is, first of all, the way most of the world thinks of a graph is something like this, okay, where you're plotting data and you've got some x coordinate and you've got some y coordinate. That is what most of the world thinks of as a graph. Computer science graphs, I guess the popular buzzword these days, sometimes they call them networks. Okay, a graph or a network, okay, is a thing defined on a set of vertices and a set of edges, okay, where each edge is either, depending upon what kind of graph it is, either an ordered or an unordered pair of vertices from the set of pair of vertices from the set of possible vertices. So we're going to be talking in here about networks. Here is an example of a network, okay? This is a road network, okay, where there are vertices, where the vertices represent cities, okay? And there is an edge if there is a direct road between those 2 cities. Does everybody see this? The vertices are cities, the edges are roads. Why might one want such a network? Okay, why would someone care about thinking about this thing as a graph? Okay, yeah. So a GPS thinks of this as a graph, okay? In fact, GPSs are amazing, amazing things, okay? I mean, I go to a store, I can buy a GPS unit for under $100. This has a network, if you wish. This has somehow stored up on it a network of all the roads in the United States, okay? Essentially every address in the United States, of which I believe there are probably millions of them, okay? And when you push the button and say, find the shortest path between pairs of things, this little GPS computer is able to find the shortest path from here to a particular taco stand in California within a few seconds, okay? And that is an amazing thing. That because, you know, in some sense because you have the network represented right, because you have the right shortest path algorithm that you're using, you can find the provably shortest path in this amazingly large network, okay? Any questions about that? Anything else people might want to do with a road network? Okay, typically we think of it as GPS to try to find the shortest path between 2 things. That makes sense. Are there any other things you would want to do with a road network?
We might assign weights to the roads and try and solve this traveling salesman problem.
Okay, so you might want to do a traveling salesman problem. Okay, let's say that you have a road network and you have a certain pair of cities you want to visit. A logical thing to do is to find the shortest tour that visits all of them. So that's another network problem on a road network. Yeah? What? Packets. Well, packets in a, packets in a road network, that's in a communications network, I would typically say. Let's say we think about road networks. Are there any other things people want to do with road networks? Yeah.
Construction, for example, they would
Okay, so one question that you might want to ask are things like, where can you add an edge, okay, to shorten the most number of people's trip? That would seem like a reasonable thing. You're trying to figure out where can you find a road that will shorten people's trips. Or if you're the Department of Transportation, you may decide to do repairs on a road so that it will inconvenience the most people. That's what seems to happen, okay? So that's sort of a notion. Anything else people might want to do with road networks? Mail delivery. Now, mail delivery is interesting. Why is mail delivery different than shortest path? Okay, yeah. You have to touch this, right? Think of all the people here who have post office boxes. Okay, again, they aren't on the highways necessarily, but you get the idea. In order to deliver mail, you want to figure out the shortest path for somebody to visit every single road network and get back to the post office again, right? This is more like an Eulerian path problem. But when you want to route garbage trucks or you want to route postal trucks, it's a different kind of a graph problem. And learning what the name of the kind of graph problems people have studied, you'll find that usually your application is one of them, basically. Okay, and that gives you the right way to think about it. Anything else someone wants to do with a road network? Snowplow. Snowplows, in principle, should be like the garbage truck thing, right? Because you want to visit every single road. Okay. Now, on the other hand, it's not quite like that because there's certain roads that are more important because maybe more people use it or a more influential politician lives on the road. Okay, and you want to plow those more quickly. But it's a variation of the same kind of routing problems that we talked about. Yeah? Okay, so what is the second longest path in the network, right? Or, here is a road, we have a blockage, now what is the best route around it? So there are a lot of graph problems that come on naturally when you model something as a graph. Electronic circuits are something else that I find is naturally modeled by a graph, okay? In fact, you can model it in a couple different ways. Here in my favorite modeling, if you view a circuit, I would view the vertices here as being junctions, okay? And there is an edge between any pair of junctions where there is a direct wired connection. And the value of that edge, okay, would be what is the electrical component here, right? These are resistors and capacitors and things like that. Is there another graph that one could think of making an electric circuit out of? Is there another way to see this thing where you might be able to model it as a graph, okay, that might be more valuable or less valuable in another way? Okay? Here I modeled it as the components were edges. Another possibility might be to model it where the components are vertices. Does everybody see this kind of a thing? And now maybe you'll decide to have an edge between any two vertices. Two components that are joined by a direct link, right? So there's going to be an edge between this. There's going to be an edge between this and this, I guess, and this and this, and this and this, and this and this. Okay? Does everybody see that you can, in this case, model the circuit two different ways? One times where the components are edges, one time where the components are vertices. Which is better? Yeah? It depends is the right answer, okay? For certain kinds of problems, it may make more sense to see it as, the components as edges, and sometimes it may take it to be vertices, okay? And the big idea in my mind, the big practical idea in using graph algorithms is thinking, how do I take my problem and model it as a graph so one of the existing graph algorithm things sort of does what I want to do, okay? This is a big picture. One thing I do, I confess, is look on Twitter to see if anybody typed my name in. That's one thing I do. And occasionally you see people take quotes from my book and they type it in and tweet it to other people. This, I think, is good to do. Okay? But one quote that people tweet a lot from my book, a lot, okay, reasonably often, is something that says, design graphs, as Skeena says, design graphs, not algorithms. Okay? That quite often, you know, this is for interview questions. It's not so much maybe for the course assignment here or whatever we're going to do. But quite often, what I find when a graph algorithm problem walks in the door, okay, very seldom is it that I solve it by designing a new graph algorithm. I think about their problem. I think, how do I model it as a graph so one of the existing things that I know about solves it, okay? And the language of graphs is rich enough that this works out surprisingly often, okay? Any questions about that? That's kind of the key. If you want to say, what is the biggest lesson of today? That is the lesson I want you to internalize. Is that when a graph problem comes in the door, think about what that graph actually means. Try different ways of thinking about how you represent it as a graph. And then which of your problems smells most like it. Okay? Any questions about that? Okay, good. Boom, 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 boom. So if we're going to say that the big picture, this biggest single thing to do in using graph algorithms in real life, okay, is learning how to model your problem as a graph algorithm. It is important to learn the notation, okay? With graph algorithms, like I say, learning to talk, learning to figure out what the graph terminology is, so that when a graph comes in the door, you can properly classify what is interesting about this graph. That is a large part of the battle here. Okay, so I'm going to spend the next several minutes going through examples of different properties of graphs. Okay, so that when you look at a graph, when I see a new graph, these are the kind of questions I have. I want to categorize it into what properties are there. Because depending upon what the properties or the flavor of the graph is, it makes a big difference on what algorithms are appropriate, okay, and how efficient something's going to be, and how well something's going to work. Any questions about that? So let's look at properties of graphs. The single most important property of a graph, okay, that I don't want. The first, let's say, direct property of a graph that comes up is whether a graph is directed or undirected. Okay? We say that a graph is undirected, okay, if edge xy implies that yx is also an edge. Okay? A graph is undirected if, in some sense, if there is a way of going from x to y, that automatically implies that there is an way of going from y to x. Okay? Certain graphs are undirected. Certain graphs are directed. Actually, are there any other graphs that people know of here? I talked about road networks and I talked about circuits. Are there any other kind of graphs in the world that people know about? Okay. Is there anything in your life that is a graph? Yes.
Critical path.
Critical path sounds like an algorithm. What is there a graph on your life? Is there a particular graph? Okay. Dressing. Okay. Let's say I don't want to go there. Okay. Anybody have? Are there any other networks or graphs in your life? Yeah. Social networks are a graph, right? That's a good example of a graph, right? And what are the vertices of this graph?
The vertices would be people, and the edges would be their friendship.
The peoples are right. You have a people, and there's an edge if there is a friendship there. Okay. Any questions about that? Okay. Are there any other networks that people know of? Has anybody else encountered a big graph in something that they do? Yes. Supplier and business networks. What might this be? Okay. So suppose, let's say, you're saying you're going to draw a vertex where here you've got a supplier, maybe somebody who sells gas, and you have consumers, people who need gas, right? What?
Sorry. Go ahead.
Okay. So you could imagine a world where there are supplier nodes and there are consumer nodes. And maybe there is an edge if this node supplies that customer. Okay? Why might someone care about a network like that? Okay, I'll talk about social networks a little later. That's why I dropped that issue. But can anyone think of analyses you might want to do on a graph where you've got a network of suppliers and customers and what their relationships are? Okay, yeah?
If you have like distributed suppliers, then you can tell where like the problem is like with the customer supplier. You can individualize it. You can check each of their gross income and see like which one is.
Okay, there might be certain issues of robustness, like for example, I mean, paraphrase what you might be saying. It may be the case that certain suppliers, there may be a lot of people dependent upon one supplier. Okay, and if so, knowing that there is a critical node here, a bottleneck, is an interesting thing to know about, right? In the newspaper, if you have, people, I guarantee you, intelligence services build graphs like this, where they know what's supplying, who's supplying what. They very much like to know who is supplying Al-Qaeda with its stuff, right? North Korea is buying its nuclear stuff. Where is it buying it? Walmart, all this kind of stuff, right? If you understood who the customer was and you understand the supply network, you want to try to piece back and understand it. This kind of a network would be a good model of a lot of different business processes. And there are natural questions you're going to want to ask on it. Any questions? Any other examples of graphs maybe before we go in here? Yeah?
All graphs in reverse engineering.
What?
All graphs in reverse engineering. Like if you open an executable up in assembly, you see the call graphs, like what functions call each other.
Oh, you're saying thinking about programs. What I'm thinking about is in software modeling. What is in software, what is an interesting graph? Okay, you've got a vertex would represent each subroutine or line of code, depending upon what your individual unit is. And certain subroutines call other subroutines. Does that make sense? That's what we call a call graph, right? And indeed, it's quite useful sometimes to look at a piece of code and to build this call graph on it. Why might we be interested in the structure of the call graph? Yeah?
So when it comes to profiling, so some subroutines can be called too frequently.
Okay, so you want to think, one argument might be a question of where is it that the program is spending its time. That's what I'm hearing. Okay, and that maybe this is helpful in analyzing where that is. Okay, any other things that you might want to do with the call graph? Yeah? Software testing is a good one. What is an important thing to do with a call graph? Well, a test is designed to convince you that your program is working, right? Being computer scientists, we know that a program is working if every line had one good test example through it. Okay, that's not quite right, but that's better than having no test case covering something. You could imagine that suppose one test case covered the flow of execution from the test case, hit those routines, and another test case, the flow of execution hit that routine, and the next test case did this. What you really want for testing purposes is a set of test cases with the property that every vertex in the graph gets executed. Okay? Is that right? That's one way you might describe a testing problem. What else is something you might do with the call graph of a program while we're at it? Yeah? Optimizing it? So maybe there are issues in optimizing it, but that's still a little obscure to me in terms of where the graph really is. One thing that's less clear to me, that's clear to me though, has to do with testing dead code. What is dead code in a program? Yeah? Code that is never used. How would you test whether a piece of code is dead? By looking at the call graph, yeah?
There's no edge between any used piece of code and that piece of code.
Exactly right. Now we imagine here's a bunch of subroutines. This subroutine calls this one. These subroutines call each other. Here is the main part of the program. these subroutines call each other. If there is no edge between this component in the graph and that component in the graph, this has to be dead code. Does everybody see that? So analyzing the call graph to figure out what the separate components are is a classic graph algorithm problem, right? So if you said design a program for dead code removal, this sounds very complicated. When I tell you it means do connected components in a graph, it doesn't sound so complicated, okay? Or do what is really a depth-first traversal from the root of this graph. See what is visited, and anything else that's not visited is dead, okay? So this is how the wily graph theory algorithm person thinks. How do I take my problem, reduce it to a graph problem, such that the graph problem is one that people know about? Any questions? Okay, so let's think of these graphs now, and let's think about directed, undirected. Are road networks undirected or directed graphs? Okay, yeah? You would say directed. Whenever, certainly within a city, a road network is going to be directed because there are one-way streets in a city, right? You can go from here to there, but there's no direct link the other way if you're to drive legally on the roads in the city, right? Now, on larger scale road networks, usually if there's a highway going one way, there's a highway going the other way, right? So you might think of the big scale road networks as being undirected, but the local, smaller, or city level ones as being directed. Okay? Any questions? Is the call graph a directed graph or an undirected graph that we had defined? Is that who here says undirected? Who here says directed? I would say it's directed because one subroutine calls another one, right? You could have a very, very important subroutine that lots of things call. It may call nothing, right? The direction of the flow of execution is what matters. So the call graph is a good example of something that is directed. Okay? Any questions? And different algorithms work on directed or undirected graphs. Any questions? Another property of graphs that's sometimes interesting is, are they weighted? Okay? In a weighted graph, we will assign an edge or occasionally a vertex, okay, an integer weight. In a road network, what is a logical weight to put on an edge? Okay, yeah? The distance. If you want to know, to try to figure out travel times, okay, knowing how long that chunk of road is would be a valuable thing, right? Is there any other weights you might want to put on an edge in a road network other than distance? Yeah?
How much traffic goes through that road?
How much traffic, or maybe I would say more generally travel time, is probably what the GPS probably wants to know. They don't care that this is a short section. They want to know that this is a short section on a Long Island, and it's going to take a long time to get through it because there's a lot of traffic. Okay? Any other road network, things you might put a road network? Yeah. Cost of tolls. Let's say you want to find the cheapest path. Okay? The cost of tolls would be interesting. Most roads are free, but that link over the Verrazano Bridge will get you, right? Okay? Yeah.
You could put the number of houses on the road in that location.
You could put the number of houses on the road, but although I'm not sure I offhand know why I would want to do that. Okay? Maybe I might not want to do that for the mail application. So if, let's say, I'm looking for a routing thing, I want to schedule my postman. It is probably slow for the postman or the garbage man on a chunk of road where there's lots of houses, independent of how long it is, right? So weights make sense in certain contexts, okay? It's not all weights, but the key question is you want to have what is the right weight for something, okay? Any questions? An unweighted graph is one where there is no cost difference. Which of the ones we've talked about so far would be an unweighted graph? Can anybody give me a good example of an unweighted graph where there probably isn't a numerical label on an edge that makes much difference? Yeah? The call graph, to me, is, for most applications, probably not that interesting. It says that subroutine A called subroutine B, okay? And, you know, for things like identifying dead code, there is no number you want on that graph that is meaningful. Any questions? So you're right. When I see a graph, I say, is it weighted? Is it unweighted? How should it be weighted for me to do what I want it to do? Okay? Any questions? Another distinction, which is, you know, maybe a little more esoteric, but still important, certainly very important if you can actually program it, is the distinction between what I would call a simple graph and a non-simple graph. Okay? A simple graph is one where the edges are between pairs of vertices where the vertices are distinct and there are not multiple edges between a graph. Okay? So this is a simple graph. It doesn't have any self-loop. A self-loop makes something simple, not simple. And it doesn't have any parallel edges here between pairs of things. Okay? Does everybody see it? In this graph, every pair of vertices has at most one edge between them. And there is never a self-loop. Okay? These are called simple because self-loops and parallel edges are weird cases for a lot of graph algorithms. Okay? And so often, you prefer your graph not to have them. But a lot depends upon the modeling. Any of the graphs we've talked about in here, can anyone think of a reason why there might be a self-loop in one of them? Yeah? A call graph with recursion would be marked by a self-loop. That is exactly right. Okay? Anybody else have any other case where there might be a self-loop? Okay? In one of the graphs we talked about. Okay? Again, these things, these things sometimes come up. What would we be looking at? Are there sometimes, let's say, turn lanes, okay, where in order to get from one place to another, okay, you basically go and take a detour and turn back. Certain road networks may have this structure, may not have it. That would be a self-loop, perhaps. Any questions? Yeah?
What about like traffic circles?
A traffic circle, okay, a traffic circle might be a self-loop, but usually not. And the reason is because a traffic circle, what would be a dumb traffic circle, is one where you go into something and then you have a traffic circle and there's no other exit than where you came in. That would be what I mean by a self-loop, right? At this point, I have the option of spinning around and around, okay? Where traffic circles are useful is if there are multiple things going into it. Does everybody see that? Okay, so I'm not sure I would call, when I'm modeling it, I don't think I'd model a traffic circle as a self-loop, unless somebody's done something weird, yeah.
So a dead end or a cul-de-sac would be a self-loop?
A cul-de-sac might be a self-loop. This is your city looks like, you have the houses here, right? And maybe you would view this as a self-loop, or maybe you'd view it as an endpoint. It depends upon what your graph is. So, what about a multi-edge? When is a graph on an edge to itself? Okay, can anybody think of a world where there are more than one edges between pairs of nodes? In anything we've talked about, yeah.
Consider service roads on highways or expressways?
So you might, when you're modeling, let's say, the Long Island Expressway, between pairs of points, there might be multiple, depending upon how you view it, you might view that as a multi-lane, as a multi-edge. If you've got a world where there are 2 points on the road and there's, let's say, the Long Island Expressway, and there is a service road that it runs parallel to it, right? Or maybe multiple lanes on the road. My GPS is smart enough, it seems, to know what lane I'm in, right? You might model that as a multi-edge, okay? Although it's not clear to me that that's necessarily the right way to do it. Any other examples? Again, these occur. If we go back to my circuit example, clear. Here on my circuit example, here I have on one of my formulations, if I was using my junction formulation, here you'll notice I have a multi-edge, right? Does everybody see that? And it makes sense. These are really two distinct things. One's a resistor, one's a capacitor. Okay? Any questions? In general, when you program these things, you got to know, is your graph simple or not? And if it's not simple, you have to make sure you're doing the right thing with your multi-edges and self-loops. Any questions? An important distinction is whether your graph is sparse or dense. Okay? And this is not, in some sense, a hard distinction, a mathematical distinction, but there is a qualitative difference. We say typically, if we have n vertices, if the number of edges, we usually say that the number of vertices is n and the number of edges is m. If m is order n, that means you've got a number of edges that's linear in the number of vertices. That we say is sparse. What's the most number of edges you can have in a simple n-node graph? Okay? If you have n nodes and n vertices and it's simple, how many edges can you have? Yeah? N factorial, no. N factorial would be a huge number. Okay? How many edges can you have? N squared is the right order of magnitude. Why is it? Each one of the n vertices can be connected to how many other vertices? N minus 1-ish. Okay? So the answer is something like n times n minus 1, or n if you're allowing loops, right? That's going to tell me that it's something like n squared, right? So you can have a quadratic number of edges, okay, in a dense graph, a linear number of edges, typically in a sparse graph. Sometimes n log n is considered to be sparse. But there's a difference between problems where almost all the pairs of edges are connected and where relatively few number of pairs are edge connected. Okay? Because usually when you measure the efficiency of a graph algorithm, it'll be a function of n and the number of edges. And sometimes there'll be algorithms that are faster when there are, relatively, the relative speed of two algorithms may differ between when you're running it on a sparse graph, which has order n edges, versus a dense graph with order n squared edges. Any questions about that? Now, what's interesting about sparse and dense, so you have to, when you see a graph, you've got to look at it in your heart and say, is it sparse or is it dense? Okay? Road networks. Are road networks sparse or are they dense? Let's think about this. Who here says sparse? Who here says dense? Okay, about half and half. I claim if dense means a quadratic number of edges, I say you can't have a road network with a quadratic number of edges. Think about it. Is it possible to have a set of cities where every pair of cities is directly connected by a set of highways? Okay? The answer is no, and why not? The main reason is because roads are generally put on the earth. Is that correct? And you don't want edges crossing each other because that requires building bridges, right? And the fact that roads are expensive to build and the fact that bridges are even more expensive to build means that you can't have too dense a road network. The degree of a vertex is the number of edges that are incident upon it. What is the intersection that you guys have seen that has the most number of roads incident on it? In Manhattan, the standard one is 4, right? It's a corner. Is anybody familiar with any other roads? Yeah?
One time I was in this small town in central New York called Hamilton, and I did see a 5-way.
A 5-way, okay. When I once asked this, if you go to my course webpage, somewhere in, I believe, Poland, one of my students pointed out to me a road where 8 roads meet in an intersection. Okay? But you're not going to get 100. You're not going to get n. Okay? 8 times n. If every intersection looked this bad, you would still have only 8n edges, right? So road networks have to be sparse. And that's good to know when designing algorithms for them. Of the other graphs that we talked about, are there any of them that are sparse? What other road network have we talked about? We talked about electrical circuits. Are electrical circuits sparse? Networks sparse? My instinct is probably yes, for the same reason. They're laid out on a printed circuit board, right? And they don't have wires going out the wazoo. You can't connect them directly. Okay? So those are probably sparse. Can anybody think of a graph that is dense? Okay, yeah?
What about like web networks?
Web networks, well, web networks are not dense. Web networks in general, each web page links to a small number of other pages. What's dense is the whole pattern of connections. Does everybody see that? The fact that every web page can reach every other page simply means that the graph is well connected. It doesn't mean it has a large density of edges, right? This is an important distinction to make. Okay? So anyone think of something that's dense, yeah? You say social networks are dense. Social networks are not dense. How many friends, Mark Zuckerberg tells me how many friends you can have. How many friends can you have? What's the maximum number of friends any of you can have? 5,000. How many people are there on the world for you to be friendly with? On Facebook's world, there's 1 billion of them, right? Every person you could you be friends with 1 billion people on Facebook? No, because Mark Zuckerberg won't let you, right? And you're not, okay, because by definition, you don't know that many people, right? So Facebook is a sparse graph. That's an important thing. Now, a lot of graphs are dense. Can anybody have an idea of a dense one? Yeah. Cellular network. If you want to say who can call somebody else, okay, let's think if we wanted to draw a graph of who could you make a local phone call to. Let's say if that may be your graph. Your vertex is a phone number. Your edge is who can I make a local phone call to? Well, I can make a local phone call to everybody in Suffolk County, right? So that would be a dense graph, right? Anybody else have a sense of a dense graph? Yeah.
You wanted to schedule multiple teams against each other, where each team is a vertex. And
Multiple teams against each other. What I would say where you tend to get dense graphs are when you have a lot of things and a lot of other things, such that you're comparing each of these things against all of those. So suppose, let's say I had a bunch of, let's say, men and a bunch of women, and I had a desirability, okay? How much is this person like, potentially like that person? How compatible are they? Now, every possible compatibility relation, there would be some kind of a possible score for. That might be a representation of a dense graph, yeah. Airports. Well, what are the vertices and what are the edges? The vertices are the airports, and the question is there a flight from this airport to the other? My instinct is most airports are pretty sparse. You go to Islip, you can't fly anywhere, right? You can fly very few places directly from Islip, right? To JFK, you can fly to a lot of places, but not anywhere near, all places. Usually you have to take multiple stops even from JFK if you want to go to Kalamazoo or someplace like that, right? So it's important to know when a graph is dense and when it is sparse. A lot of what we've proven here is one thing I say. With application-specific constraints, usually graphs are sparse, okay? And that's going to drive some of the data structure issues of what we do with graphs. Any questions? Yes? A complement of a graph is where we take all the edges and replace them by non-edges, and all the non-edges and replace them by edges. And yes, if you have a sparse graph and you take its complement, that's going to be a dense graph. That's exactly right. Okay? So sometimes you may want to work on the complement of a graph. Okay? Let's say I want to find the shortest change of non-friends between me and the president. Okay? Actually, I guess it's one. It'd be one edge, me to the president directly. Okay? Then, anyway, complement of a sparse graph is dense. That's a good example. Any questions? Okay? And so learning to think like this is what is important about graphs. Another issue is cyclic versus acyclic. A graph is cyclic if it has a cycle in it. Here, I believe this is a cycle because I can go from here, ka-chung, to there, ka-chung, to there, ka-chung, to get back to another place. If a graph has a cycle, it is called cyclic. If a graph does not have any cycles, okay, it is called acyclic, okay? And a lot of graphs, what is an undirected graph that doesn't have any cycles? What is that graph called? You guys have heard this word a lot. What graph is it? It is undirected, that is acyclic. What is it? Yes? It is a tree. The fact that trees are an important thing. Why are trees an important thing? Because they are acyclic graphs. That's really one of the things that it's one of the properties of trees that makes them interesting. Okay? So when you have a graph, certain things have no cycles in them. Okay? Any questions about it? An undirected graph that has no cycles is called a tree. A directed graph that contains no cycles is called a directed acyclic graph, which we pronounce as a DAG. Okay? So we're going to use this word often enough, we're going to give it a name. A graph that is directed but acyclic is called a DAG. What graphs can you think of are DAGs? Can anybody think of a world where there is a directed acyclic graph? Yes? Job schedule. Or what I would say course prerequisites. It's a similar kind of a thing, right? You're taking 373. This may be a prerequisite. This is a prerequisite for this was CSE373, right? This course is a prerequisite for success in life, right? You can imagine a world where every vertex is a course. There is a direct edge between any things where one is a predecessor of the other, right? Why does this have to be acyclic? Okay? Yeah?
Because if you can't have something be a prerequisite for each other, otherwise you can't.
Think what would happen if we designed our curriculum where this was a prerequisite for this, which was a prerequisite for this, which was a prerequisite for this. No student could take any class. Okay? Maybe it's a professor's dream. Okay? But does everybody see that if you have a precedence constraint, you cannot have cycles in it? By definition, an interesting graph like that has to be acyclic, okay? And when you have a graph, you've got to smell, is it acyclic or not? Because there's different algorithmic issues of whether it's going to be acyclic or not. Any questions here? Yes?
You could take alternative courses for a course prerequisite. So, for instance, instead of 303, you could use 350. So, in that case, would you model that with a different kind of DAG?
Well, wait, no. Again, okay, so you're saying now, what if you're allowed alternatives, that I can either this or that? Now you're telling me there's some logic on the edges, right? The prerequisite for this course is either A or B. Then it's not really just the graph structure. There's some auxiliary information that you need to know to interpret that graph, okay? So that moves it a little outside the flavor of a pure graph problem, okay? Any questions? What other distinctions are there? Let me talk about, there's a couple of these. We're running low. I encourage you to read the book about it. One other distinction that turns out to sometimes be important is the distinction between a labeled graph and an unlabeled graph. In a labeled graph, each vertex has a unique name, okay? And in an unlabeled graph, it's just a topological structure where a vertex has an ID, okay? So, it comes down to this. If I have a graph that looks like this, where this is vertex 1, 2, and 3, and I have a graph labeled A, B, and C, are these two graphs the same graph, or are they different graphs? If you ignore the labels, they are the same graph. Does everybody see that? They have the same structure. If you treat the labels as important, they are different graphs. Sometimes the structure, the labelings of graphs matters, sometimes it doesn't, okay? And so when you deal with it, you have to think, does the name on the label mean anything? Okay? Any questions? Anyway, I encourage you to go through the, the textbook. I describe some of these other properties. Learning to tell what a graph is or is not is important. So let's just get one last review of these things, okay? When I think about social networks, I think of it as the friendship graph, okay? Vertices are people. This is a social network. Vertices are people, Edges are friendships. How can we interpret these things? What kind of algorithmic questions might come up on a social network? The first question is, that I think is kind of important, is again, when we talk about direction, okay? Is it true that a social network is directed or undirected? Which is it? Okay, is Facebook a directed graph or an undirected graph? Yeah? Undirected. Facebook is undirected. Why is Facebook undirected?
Because relationships really don't have
They have to be, to be, if I'm your friend, you have to be my friend. Is that true in life? Not necessarily, okay? Certainly, is the herd of graph. Let's think about the herd of graph, where there's an edge from x to y if x is herd of y. Is that a directed graph or an undirected graph? Well, the herd of graph. Have I heard of you? Is that a directed graph or an undirected graph? Directed. Okay, I have heard of Sylvester Stallone. Sylvester Stallone has not heard of me, right? What about the had sex with graph? Okay, this is another example. Okay, is that a directed graph or an undirected graph? Okay, as I understand these things, again, I don't want to go into these things. I think of this as an undirected graph. Because if x had sex with y, y had sex with x. This is my understanding of things. Any questions? Good. Am I my own friend? Okay. In Facebook, can you be your own friend? No. Okay. Can there be two friendships between people? Okay. In Facebook? No. In real life, can there be two friendships between people? Well, yeah, kind of sometimes. It depends, right? Maybe I know you from high school, and I know you because you're also studying computer science, right? So if I labeled each edge represented a reason why you're friends, okay, that might be a multi-edge, right? But as far as Facebook's concerned, okay, Facebook graph is simple because it doesn't allow you to be your own friend, and it doesn't allow multiple friendships. Whether that's true depends upon the phenomena that you're trying to model. Any questions here? What other kinds of things might we want to know? Okay. Typically you want to know, like the 6 degrees of separation thing. Is there a path from me to some famous person? Okay. And this is a problem that, again, this is a problem about finding a path in a graph. Ideally, to impress somebody, you want the shortest path. Any questions? Any questions about what these graphs are and how we model them? Any questions? Okay. So the rest of the time, what I'd like to talk about here is, how we would represent graphs. Okay? There are two main data structures that you need to represent graphs. Okay, there are adjacency matrices and there are adjacency lists. I want to show you what these two basic structures are. Both are sometimes very useful. One turns out to be better at representing sparse graphs, and one turns out to be better at representing dense graphs. That's the biggest distinction between them. Okay? The adjacency matrix is the one that is best at representing dense graphs. Okay? What is the situation? Again, we are always going to use this assumption that graphs have n vertices and m edges. So I'm not going to define that again. N means vertices, m means edges. Okay? The way that an adjacency matrix works is we're going to define a number of vertices by number of vertices matrix such that element ij is going to be 1 if there is an edge from I to j, and it's going to be a 0 if there is not an edge from I to 1j. Okay? So every edge is going to be represented by one entry in the matrix. Okay? Any questions about that? Okay, so I think I have, do I have an example on the next slide, or am I? No, it's so easy I didn't bother to do that. So what's the real idea here? You've got a matrix, ij. Here we're going to ask ourselves, true or false, is this edge there? And it's either going to be true, 1 if it's true, and 0 if the edge is not there. Any questions about it? So let's think a little bit more about it. What could we do? Could we save any space if the edge is undirected? If we have an adjacency matrix, we're going to have a 1 whenever there is an edge from I to j. What does that mean about an undirected edge? Yeah? That is, if there is an edge from I to j, there is an edge from j to I. That's what an undirected graph means. So do we need to allocate n times n memory if we wanted to represent a direct, undirected graph? Or might there be a better way to do it? A maybe more efficient way to do it? Yeah? What we could do is just represent somehow half the matrix, right? And then if I want to know, I'm going to have, let's say I'm only going to represent it where I is less than j. And now if you ask me about edge 1, 3, I'm going to go to row 1, element 3. If you ask me about edge 3, 1, I'm going to say, wait a second, I need I less than j. I'm going to look at 1, 3, and I'll look at the same spot. Does everybody agree that we could conceptually represent an undirected graph with half as much memory and still get seemingly the benefit of the adjacency matrix? Any questions about that? Now, it's a little hard to allocate maybe triangular arrays, and we only deal with the big O, and in this class we don't worry about wasting half the memory. But maybe your boss will if you work at Facebook, okay, or something like that, in which case you got to think about these things. Any questions? Okay, good. So that's an adjacency matrix. What is an adjacency list? An adjacency list is a data structure for representing sparse graphs that is going to consist of 2 things. It is going to be an array of linked lists. The array part is important, okay? What we're going to do is let element, if we want to look up edge ij, we're going to represent edge ij by being an element, j, somewhere within the ith linked list. So each vertex from 1 to n is going to have an array, there's an array from 1 to n. The ith element here is the linked list of edges coming out of the ith vertex. Does everybody see this? So if we take a look at this particular vertex, vertex 4 has an edge from 4 to 2. Here we've got it. It is an edge from 4 to 5. There we got it. It is an edge from 4 to 3. There we got it. Those are the only elements on that linked list. Does everybody get that idea? Okay. Now in an undirected graph like this one, there is an edge from 4 to 2. There is also an edge from 2 to 4. The edge from 2 to 4 is represented in the second list. There is an element 4 there. Okay? Any questions about it? Does everybody see that in this basic representation, we are representing each edge twice in the adjacency list? If it's an undirected graph, we are representing each edge twice. Okay? If it's a directed edge, each edge is represented once. Any questions about that? Okay? Any questions about that? Okay? So let's think about that. How much time does it take to test if edge ij is in the graph? Okay? How much time is it? How would we test whether edge ij is in the graph? Okay, yeah? First, let's say, how do we do it? Okay, and then how long does it take?
Go to position I in the array, and then traverse through the linked list until you find if j is there.
Okay, so how much time does that take? O of k, where k is what?
J.
O of j, it is not O of j. Okay? Okay, so let's think. If I look for edge ij, it is not going to be order O of j, because j is the number of that other vertex, right? It could be that you talk about the last person in the array, who happens to be, number 6, right? That person may have no friends, right? So it's not that. What is it?
It's order k or whatever other letters, such that that's the length of the array.
It is order proportional to the length of the list, which is the degree of the vertex. We have to learn this word. The word is degree. We say that the degree of the vertex is the number of edges coming out of it, right? Looking up whether edge ij is in the adjacency list takes time proportional to the degree of I. Okay? Any questions about that? So let's have a comparison quickly among the adjacency lists and adjacency matrices to decide which is better. Okay? Which is better? Which is faster to test if a particular edge is present? Okay? If I want to know, are Brad and Angelina friends? How do we do this? Okay, in an adjacency matrix, it would take how much time? If we know the index of Brad and the index of Angelina, how much time? O of 1. And how much would it be in an adjacency list? O of the number of friends that either Brad or Angelina have, right? The degree of those vertices. Which is faster to tell how many friends Brad or Brad has? Okay? How much time in an n by n graph in an adjacency matrix does it take to tell how many friends Brad has? N. Why is it order n? How do you find the degree of this vertex? I go to the row, Brad's row, and I go bop, 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 okay, and say if I see a 1, it's a friend. I count how many 1s are in that row. That is order n. How much time does it take to find out how many friends Brad would have if I had represented it by an adjacency list? How many? Could be constant, you say. It depends upon how many friends they have, right? Okay, if I kept an auxiliary field, then I could just look that up. But if I wanted to compute it, it means looking through the linked list, right? So the natural thing is, it would be time ordered the degree of the vertex, which in general is less than n. So linked lists win. Any questions about that? Which uses more memory, less memory on sparse graphs? Okay? If I have a graph with n vertices and m edges, how much space does it take for an adjacency matrix? For m edges in an adjacency matrix on n vertices, how much space does it take? If I want to represent this graph with m edges, n vertices, I have an n by n adjacency matrix. How much space does it take? N squared, right? Even if nobody's friends, okay, it's n squared, right? How much space does it take on an adjacency list? Okay? I claim that it is n plus m. I need an array of size n, my array of linked lists, correct? Every edge itself, okay, is going to be represented once or twice by nodes in the linked lists. So it is order n plus m time, and on a sparse graph, lists win. On a dense graph, matrices have a slight win. Matrices would be n squared, so would lists. But I guess you're wasting a lot of space for pointers. That's why I say it's a minor win on a dense graph for adjacency matrices. Which is faster to insert an edge or delete an edge? How would we insert an edge into an adjacency matrix? What do we do to insert edge ij into an adjacency matrix? Yeah?
We have to go to both the linked lists for both I and for j and insert the adjacency.
Okay, in an adjacency matrix, we're just flipping a bit. Does everybody see that? That takes constant time. To insert or delete an edge, I've got to go to the appropriate lists, and if I'm deleting an edge, I've got to find where in the list it is, right? So these kind of things tend to be order degree, okay? Which is faster to visit all the edges and vertices? Well, there's less stuff in an adjacency list if the graph is sparse than in the adjacency matrix. So on a sparse graph, you're better off with an adjacency list. For most of what we're going to do, and both things are useful, both are worth knowing about, both are things going to be in the next daily problem. But which is better in general on most applications that give you richer algorithms and are much more space efficient? Usually adjacency lists are the winner. And so most of what we're going to do in here is going to be on adjacency lists. Any questions about that? Okay, very good. What I'd like to do now is we have the midterms back. Okay, let's bring the midterms in. Are these sorted by names? Okay, so I'm going to do one of two things for you, which is what I think I want to take a quick poll. We have a small amount of time, unfortunately. We could either use the next 15 minutes to pass the exams back, okay, or I could start to go through them and then you pick them up at the end of class. Which would people rather do? Okay, who here would rather I go through the test now?
Are they sorted?
They're sorted, okay, but it's still this. Looking at this, by the time it takes this many bodies to actually do something, okay. Would you rather I go through the papers now and you pick them up later, okay, or rather I not go through the answers? Who here wants me to go through the test? Who here wants me to not go through the test and just give me? Okay. So in that case, that's going to be true. Okay, so what I want you to do is to take a look at your papers. I'm not going to then go through them, okay, unless everybody has picked up their papers properly. So here's what I want to do to give them back. Okay, Hadi, you are the A through M side. This is the A through M side of the room, and Hadi is going to give them back to the A through M people. So try to sort yourselves. Come on down. If you are N through Z, you're on this side of the room. Okay? Okay, and I'll give you I will prepare this histogram of grades. Hold on. And maybe at the end I'll go through it very, very quickly if we have time. Okay. I'm now going to write the stats up here. Hold on. Okay, come. Okay, now. Yes, sort yourselves alphabetically and start passing them back. And the way that I normally do this is if the first person in line is not the first person on that I'm giving a test to, wave them by, okay, and just keep going through the list. Quickly. Sort yourselves alphabetically. Sort yourselves alphabetically within each group. Ask your neighbor. Do a bubble sort. Locally sort yourselves so you can get these back. Otherwise, this will take a week. Okay, I think the high, I think it was down to like a 20. Okay, please hurry up and pass these things back. Okay? Okay. People, let me make this simpler for you guys. You guys have to be in sorted order, and I'm going to call the name. And if you're not first in line, you don't get your paper. Go. Akira. No. Augustine. No. Ali. No, you're not close. You're close enough. Asif. No. Bordowitz. Okay. Bako. Byrek. Cow. Last name. I'm going to turn this off now, just to be sure. Let me hold on. A Canon. Okay. Let's just quickly go through the distribution. The high was a 99, the low was in the 20s. I remember it as 27, but I might be wrong. The mean was a 55. What does this mean? Everything is going to be curved, okay, at the end. So this absolute score doesn't mean anything to me, okay? If you come back to me, you don't say, oh, I got a 55, I'm failing. If you got a 55, you're not failing because you're at the mean, right? You know, I will curve it at the end, exactly what the scores mean. You know, think in terms of where they are compared to the mean, compared to the rest of the distribution. These are obviously very good. These are obviously very bad, okay? If you're doing very bad, then you need to figure out why and what you can do better on the next test, okay? Any questions about the distribution and what it means? Okay? Any questions about that? A 60 is better than a 58. That's the direction you need to know. Any questions? Okay, let's go through the problems very, very, very quickly. Okay? Again, the first one should have been relatively straightforward. It has to do with ranking the complexity of the functions from biggest to highest order, lowest to highest order. There is, and then proving something big O-wise. That should have been relatively straightforward. Any questions about that problem in particular? That's one I don't think is very complicated. The data structures problem, homework from 2 was on the homework. You set up an array, a bit vector. Is this element in the array or not? Depending upon whether it, you know, inserting it means twiddling the bit, deleting it means twiddling the bit, search means checking the bit. The third one is an interesting one about the fragile elements. What is the basic vision here? The basic vision should be, the real question, is there any element in here that is involved in a large number of comparisons? In quicksort, regardless of how you do it, it's obvious that there is one element that is involved in a large number of comparisons. It is the pivot. It has to compare itself against every other element in the array. Does everybody see that? There's n comparisons involving the pivot. That's the first 2. In merge sort, what is going to happen in merge sort if the elements were originally sorted? Well, you're right. There is a logarithmic height tree, and each element is involved in a logarithmic number of merges. But what happens if it's sorted? The first thing you're going to be doing is you're going to have this list of elements from 1 to n over 2, and this other list of elements from n over 2 to n. The first thing you're going to do to merge these lists is to compare this element against this, and this is going to be first. And then you're going to compare this element against this, and this is going to be first. The head of this list is going to be compared against n over 2 times. Does everybody see that? So if the elements are sorted, the act of merging the 2 lists, the head of the second list will break if it's too fragile. Now, if the elements are random order, then this phenomena isn't going to occur. Okay? In average, when you merge these things, okay, the gap between, you know, the number of elements, if you look at 2 elements on this side of the list, the number of elements that should be on this side, it's flipping a coin. It's the number of times it came up heads in a row before you got one that came up tails. You won't have large runs of heads. And so that one, in fact, on average, a logarithmic number of elements will be needed if it was random. That's the theory behind that problem. Any questions about that? Let's move on. For the mode, how do you calculate the mode? The mode was the easy, efficient algorithm is one where the elements are sorted. Okay, as you sort them, it takes n log n, and then it's you scan them and you look for the biggest chunk of elements. That's the first part. The second part asks, what about the case where one of the elements occurs more than half the time? Now, if you sort it, that's not going to be linear. Okay, if you assume it's sorted, that's wrong because it doesn't say it's sorted. Okay, how might you be able to do this? Well, I tell you first of all, for partial credit, you could say expected time. If you used a randomized thing to find the median, like, for example, a problem on the second homework, Okay, I asked you for an expected time thing. If you invoke that, it should be noticed that the median element is going to be the one that you want here. If one element if in sorted order, if one element occurs more than half the time, it is going to be the median. So something that finds the median would work, okay? If you know about median finding, that'd be one way to do it. The other idea is to do the following. Let's keep two piles of the elements. Let's say the elements we want to find there's 1, 2, 3, 3, 3, 3, 3, 1. What's the mode going to be? Well, if we have enough 3s where they make up a majority, we'll put 1 in one bucket, 2 in another bucket. If these two are different, if we delete these two, the majority element is not going to change. Okay? Because it's in more than half of them. If one of these was the majority element, if we delete these two, then the majority element will still be the majority element of a smaller one. The next one we have is 3. Then another 3. Let's say the next one we had was a 1. 3 and 1, we delete them. 3, 3, 3, 3, 1. We delete, whenever we have two different elements, we delete both of them. Okay? We will never have more than 2 piles, okay, that are non-empty. The one survivor that remains will be the majority element. Any questions about that? It's a little bit clever, but you get the basic idea. That's how I would do that one. Okay, the last one has to do with binary search tree insertion and deletion, stuff like that. How do you find the kth smallest element if I give you a tree of height h in this balanced thing? The basic idea would be you could call min n times, and then delete the min. Oh, that changes the tree. A little bit nicer is to find the min and then call the successor k times. And then by doing that operation, if each runs in order h time, that's k calls to successor k times h. That's the first part. Any questions? For the second one, what is the idea? Each node here